So here's an outline of the topics that we're going to be discussing related to software testing. We'll start once again with why testing is important, because I feel it's necessary when talking about anything to first say why it's important. We'll establish some vocabulary, the different types of tests. I'll go over some testing tips, and once again talk about how Turlinos is tested, since we've established Turlinos is my universe. We'll talk about code coverage tools, and then software verification. I'm going to tell you a couple anecdotes about why software testing is important, meaning a couple anecdotes about really bad things that happened because people weren't testing their code adequately. First story we're going to talk about is that of the protein structures of Jeffrey Chang. Jeffrey Chang was a scientist, I believe a biologist, who was working on generating protein structures. He inherited some code that accidentally flipped 2 columns of his data set, inverting an electron density map. So he got incorrect protein structures out of this code. He didn't notice immediately and published papers based on this code 5 times, and he ended up having to retract those 5 publications. Not only did this damage his reputation, but one of those papers was cited 364 times. So 364 groups of people based their work off of his incorrect results. The other side effect of this incident was that many papers and grant applications that conflicted with his results were rejected because, of course, they're wrong, since his results are correct. If they conflict, then obviously the other results are wrong. The second story we'll talk about is the 42nd flight of the Ariane 5. The Ariane 5 was a European orbital launch vehicle meant to lift 20 tons into low Earth orbit. Note that I say it was meant to lift 20 tons into low Earth orbit. Not super successful at that. The initial rocket went off course, it started to disintegrate in the Earth's atmosphere, and then it self-destructed less than a minute after launch. What happened is that there were 7 variables at risk of leading to an operand error because they were converting from floating point numbers to integers. Never a particularly great idea. And 4 of these variables were protected by assertions. The other 3 were not, for whatever reason. The investigation that resulted, because obviously there was an investigation, concluded that there was insufficient test coverage, and that was one of the causes for this accident. This resulted in a loss of almost $400 million. The last story we're going to talk about is the Thirac 25 accidents, which some of you may have heard of because it's one of the most famous software testing failures. The Thirac 25 was a computer-controlled radiation therapy machine that had minimal software testing. And if there's any machine that you want to have more than minimal software testing, it's probably going to be a radiation therapy machine. There was a race condition in their code that went undetected because they didn't have enough testing. So unlucky patients were struck with approximately 100 times the intended dose of radiation. They were supposed to get maybe 200 rads. They instead got 15,000. And some of you might be thinking at this point that that sounds like enough to kill a person, and you would be correct. The Thirac 25 was recalled after 6 accidents resulting in death and serious injuries. And by serious injuries, I mean things like injuries so bad that they resulted in hip replacements and other major invasive surgeries. Another issue with the Thirac 25 is that when the machine malfunctioned, it produced an error code that indicated no dose of radiation was given. So the operator had absolutely no idea that they were killing these patients, and the operator instructed the machine to proceed, because this machine produced errors all the time, and the documentation gave no indication that these frequent malfunctions could place a patient at risk. So remember when we talked earlier about why documentation is important? This is another reason why documentation is important. OK, so now that we understand how important tests are, we'll talk about the granularity of tests, meaning how much code does a particular test cover. The smallest ones are unit tests. Those are meant to test individual functions or classes. They build and run fast, and they're meant to localize errors. So the goal of a unit test is, if a unit test fails, then you should know exactly what has gone wrong in your code. You know that there is an issue in this class, or there is an issue in this function. Integration tests, they test the interaction of larger pieces of software. They're also important, because maybe all of your unit tests are passing, but a couple pieces of the software don't interact in the correct way. And then there are system-level tests which are at the highest level. They test the full software system at the user interaction level. So they test what the user wants out of the software. These are the different types of tests. First of all, there's verification tests, which check, does the code implement the intended algorithm correctly? These tests check for specific mathematical properties. For instance, maybe you're making a Krylov solver code, and you know that your particular linear system, your matrix, has a particular set of eigenvalues. And based on that set of eigenvalues, you should converge in 5 iterations. So you can make a verification test with that matrix that says, did I converge in 5 iterations or around that number? Acceptance tests, these assert acceptable functioning for a specific customer, and they're generally at the system level, which is the highest level we talked about before. Regression or no change tests, they compare the current observable output to some gold standard. But what makes them different from verification tests is that you must independently verify that the gold standard is correct. So maybe that gold standard comes from a previous run of your code, and you just want to make sure by running this test that your code has not changed, that it produces the same output as it did before. Performance tests have absolutely nothing to do with correctness. They focus on the runtime and resource utilization of your code. Maybe you've made some changes to your code and all of your tests are passing, but now your code is 20% slower. So this sort of testing is very important to identify cases like that. Installation tests verify that the configure, make, install process worked as expected. These are important for the users because from your end, maybe everything works OK, but when the user tries to link to your code, it doesn't go as expected. Now we're going to talk about some specific testing challenges that are kind of unique to the computational science and engineering field. First of all, we have floating point issues, which means that you can get different results on different platforms. And you can also get different results on different runs due to multiprocessor computation. So because the order of operations is non-deterministic in these parallel codes, you can run it twice, get slightly different results. And where this becomes an issue is that ill conditioning can magnify these small differences. So your final solution could be dramatically different if your problem is ill conditioned. And if you're testing your code saying that the solution needs to be this, it needs to converge in this many iterations, the number of iterations may be different because of that ill conditioning issue and the floating point, the different results that you got because of floating point arithmetic. Another floating point issue is that when you get two numbers that you want to compare, how do you compare them when they're floating point numbers? A lot of people do diff, meaning they do a character by character comparison of these numbers. Doing a diff on floating point numbers, not a great idea because of these floating point issues that I mentioned. Another CSE testing challenge is that of non-unique solutions. Maybe you're trying to solve you're trying to find the root of a function, and that function has many roots. So you can't just write a test in that case saying, I want to find this particular root. If I get anything other than this particular root, the answer is wrong because there are many roots. One more challenge is scalability testing. It's difficult to get accurate data on a shared machine. How many of you have shared machines through your university or workplace? If you were to run your code at 2 in the morning versus 2 in the afternoon, do you think you would get the same timing results? I'm seeing a lot of shaking heads now. Depending on what your university is, I don't know, maybe you would see more people on at 2 in the morning versus 2 in the afternoon, but who knows? It's difficult to get accurate data on a shared machine for that exact reason. The resource utilization is different at different points in the day. So instead of using a shared machine, you probably want to use a parallel machine, such as the ones at NERSC. But the problem there is that many supercomputing facilities, first of all, discourage routine scalability testing. That's not what they want their resources to be used for. And getting access to that many processors is expensive because you pay by the hour. And large jobs may sit in the queue for quite some time. One more problem is, how do you scale a problem for a weak scaling study? We're going to increase the number of MPI processes, and at the same time, we're also going to increase the size of the problem. That's a weak scaling study. A strong scaling study, in case you've forgotten, is where the number of processes increases, but the size of the problem remains constant. But there's an issue now in how you scale the problem for weak scaling studies, because how do you make a bigger problem? If your problem is based on a mesh, then you can always refine the mesh to get a bigger problem. But is that going to have the exact same mathematical properties? A more refined problem might not have the same condition number as your smaller problem. So you've now introduced a difference in your tests that has nothing to do with the number of MPI processes. We're going to talk about some testing tips. First of all, the ideal time to build a test suite is during code development. There are many reasons for this, one of which is I know I personally, if I am able to check in some code that I don't have tests for, I might not go back and write those tests because something else will always seem more important. So it's a really good idea during development to build your test suite at the same time as the code that you're developing. And at Sandia, for the Trilinos project, we frequently reject new features if they don't come with tests. So the other nice thing about building the test suite during development is that this ensures new code does not break your existing functionality. What this means is maybe you have a code that does a matrix vector multiplication, and you want to modify it to make it faster. So it should still produce the same result, but you're just hoping that the code performs better. If you already have tests for your matrix vector product, then you can use those to ensure that that the changes you've made to your code didn't break anything, that you're still getting the same results. Failing tests should help you identify what part of the code needs to be fixed. If you have a testing suite and one of your tests starts failing and that gives you no information whatsoever, then that's not good. You need some mixture of unit tests and system-level tests to ensure that when something breaks, you know exactly what it is. Software should be tested regularly. It's a good idea to set up nightly testing or continuous integration testing. You need to develop a consistent policy on dealing with failed tests. At Sandia, we like to use an issue tracking system. It's important to know who is responsible for fixing that failed test so that it gets fixed quickly. And once you deal with a failed test, you can add a regression test to make sure that you don't reintroduce that exact same issue later. It's a good idea to run a regression test suite when checking in new code, and I'll talk about that a little bit later when we talk about what Trilinos does. As I mentioned before, zero diffing tests, meaning tests where you diff two quantities and make sure that they're exactly the same character by character. Those tests are not great for our type of situations where we have floating point arithmetic. Instead, you can use a product called SPIF, which is the exact same as diff, except you specify a tolerance and you say that these two quantities are the same if they're within this distance of each other. So back to Trilinos. How is Trilinos tested? We have 1,500 tests total between our 66 packages, and developers are strongly advised to run a check-in test script when committing. The check-in test script detects which packages were modified by your commits, and then it determines which things you could have potentially broken. So for instance, I live in my eigenvalue land, and I frequently touch Anasazi, the eigensolver package. When I touch Anasazi and I run that check-in test script, what happens is it determines that I have touched Anasazi, and then it looks and it sees what depends on Anasazi. And it'll notice the package Zoltan, the reordering package. That depends on Anasazi because some of the routines are based on the Fiedler vector. So it will determine that I could have possibly broken Anasazi, and I could have also potentially broken Zoltan. And then it will see what else could you have broken, what depends on Zoltan. And it will compile and run all of those tests. So it configures, builds, and tests those packages that you could have potentially broken. And if it succeeds, it pushes to the repository. If something fails, it reports why it failed. So if it's a build error, it will tell you this is the exact build error that I got. If it's a failing test, it will tell you this is the test that failed. This check-in test script is useful for ensuring that your changes don't break another package. This goes back to the little bubble that I live in. I'm relatively new at Sandia, and if I'd been there for 20 years, then I would probably know all of the packages of Trilinos. As it is, I've only been there for a year, so I can't even name all of the packages of Trilinos. So when I touch a thing, it is reasonably likely that I could break somebody else's code and not know it. But the check-in test script is nice because it will automatically detect which things I could have broken and run those things. So it will run packages that I'm not entirely sure what they do, but that I could have broken with my changes. Because the script runs so many tests based on what you've touched, if you touch one of the lower level packages, then it might run all 1,500 tests. Because the check and test script might run all 1,500 tests, this can take a bit of time, but most of us at Sandia, we just run it overnight, and it's not really obstructive to our work. In addition to the check and test script, we also have automated testing on a variety of different platforms. So you might be wondering at this point, what is the purpose of the automated testing if everyone uses this check and test script? First of all, it might check a different set of packages. For instance, at one point, I accidentally introduced a dependency between two packages that were not supposed to have a dependency. And when I ran the code on my machine, I had both of the packages enabled, so everything worked just fine. And then the automated testing didn't have one of those packages enabled, and everything broke. So that was important. It can also test different environments than the one that you personally use. For instance, maybe your changes work with the GNU compilers, but they don't work with Intel. Maybe your changes work on Linux, but they don't work on a Mac. Maybe your changes don't work with CUDA. I've personally broken the CUDA build several times and gotten notified about it because of the automated testing. The automated testing is also nice because it identifies a small set of commits that could have broken a build or test. At Sandia, we average about 12 commits per day to Trilinos. So assuming that we only had nightly testing, we do continuous integration testing, but assuming we only had nightly testing, if a test were succeeding on March 13th, and then the test started failing on March 14th, we would know that it was one of those 12 check-ins that broke that test. And this helps to identify the person who broke the code, and it's not for the purposes of shaming them, it's for the purposes of identifying the person who knows how to unbreak the code. Bugs are also easier to fix if they're caught early, and that's the purpose of this automated testing, to catch the bugs early. I know that I personally, if you came up to me today and said, you broke a thing yesterday, I would know what I did that broke the thing. But if you came up to me 6 months from now and said, hey, back in July, you broke something, I would have absolutely no idea what you were talking about. I might not remember the projects I was on in July. So it's important to catch people early when they introduce a bug. So at this point, you might be thinking, you guys have 1,500 tests, that's great and all, but how do you possibly motivate somebody to write all these tests? Since we already discussed this morning that there are constraints. There are things that we are paid to do and things that we are not paid to do. There are things that we're rewarded for and maybe not rewarded for as much. When I was hired at Sandia, my manager motivated me to write tests by telling me that the tests were going to protect me from other people breaking my work. I was still in grad school at the time, and he said, I'm sure you want this code to continue working so that you can publish your results and graduate and leave. So, and I really wanted to graduate, so I wrote those tests so that nobody would break my code. Our unofficial policy at Sandia is that if someone else's changes break your code, that person is responsible for fixing it. We help each other. If one of us breaks somebody else's code, then we usually team up and find the solution to that problem. But it's not solely your responsibility to keep your code working. It is other people's responsibility to not break it. At Sandia, we also frequently reject new feature commits if they don't have tests with them. So that's another way that we motivate people to write tests. We just refuse to accept their code until the code has tests. And also, you might already have some tests laying around and just not even notice. For instance, some of the tests that we have in Trilinos are drivers for generating conference or paper results. All we did is took some drivers that we were using for making conference results and reduced the problem size. So if you have a file that, if you have a driver that reads in a matrix market file and then does things with that matrix market file, then just read in a smaller one, and you have a test. We also take user-submitted bugs. When a user submits a bug on our GitHub page, we usually ask them to give us a file that reproduces the issue. And after we fix the bug, we add that to the repository as a regression test. If you ever watch the Trilinos tests run, which is a great time, by the way, you might notice that some of the tests are named bug 6437, bug 2548. And they have funny names like that. And that's because back on Bugzilla, those were the names of our bugs. That particular test was a regression test for bug 2437. Also, you can take an example code and add a pass-fail condition and have a test. So if you ever look through the Trilinos repository and see that some of our example codes that are listed on the Doxygen site have a funny pass-fail condition at the end, that's what it is. We took an example, we added a pass-fail condition, and now it's a test, as well as an example. OK, so maybe you're willing to write tests at this point, but you don't know what tests you should be writing. You don't know, you have some tests, but you don't know which other tests you need. And one thing that can help you identify what parts of the code are not being tested are code coverage tools. Can you please raise your hand if you've ever used a code coverage tool? OK, we're going to learn things. This is good. gcov is a code coverage tool that exposes parts of the code that are not currently being exercised by your test suite. gcov is a standard utility within the GNU compiler collection suite, and it counts the number of times each statement in your code is executed, and it displays how many times each statement was executed. We've already established that I love GUIs, so what we're actually going to talk about is a GUI called lcov, which is a graphical front end for gcov. And it's available at that website listed below. We're going to talk about Linux tools, but there are similar tools for Mac and Windows. I just picked Linux tools because I figured that's the system that most of us work on. So here's how you use lcov. You compile and link your code with the coverage flag, and it's a really good idea to disable optimization. Does anyone know why it would be a good idea to disable optimization?
Compiler will rearrange your code.
Compiler will rearrange your code, absolutely.
It'll delete the stuff that it knows. If it can figure out it's not going to hit a part of the code, it won't even build that into your binary.
Yep.
Which is what you're trying to find.
So the compiler would do, it will do smart things to your code. It will combine some lines of code. If it detects that those lines of code should be combined, it can get rid of things. So in the interests of getting a more accurate depiction of what lines of code are being executed and aren't being executed, it's a good idea to disable the optimization. So after you compile and link your code with the coverage flag, you run your test suite as you normally would. So maybe if you're using ctest, you just type ctest. If you're using a script to run the test, you run your script. And after that, you collect the coverage data using lcov. Then you generate the HTML output using gen.html, which is part of lcov. So here's a simple example code. I have a function that I want to test, and that function is called isEven. It does exactly what you'd expect it to do. It determines whether an input integer is even or odd, and it returns a Boolean accordingly. I wrote a test for it, because we're all about testing the code now. And in this test, I determine whether the number 8 is even or odd. If it says that 8 is even, then I say, good, the test passed. If it says that 8 is odd, then the test fails. And we're going to determine whether I have covered all the code with my test. So we compile and link with the coverage flag, run the test, collect the coverage data using lcov, and generate the HTML output using gen.html. This is what our code coverage report looks like. So it gives you a percentage of, it gives you some statistics about the code, like this is the number of lines in your code that exist. This is the number of lines that got executed. Here's the percentage of the coverage of your code. And then it lists all of the different file names, and we're going to click on isEven.hpp, because that's the file that we're testing. So this is what we see for isEven.hpp. There were 4 executable lines in that code, and we executed 3 of them. We called the function, we checked that condition, and we returned true. This other case was never, ever executed or tested. So what can we do to maximize our code coverage here? Do we need more tests? We need another test. We're going to test the case where x is odd. OK, so this time we have the number equals 7, so we have an odd number. And we're going to test the code based on that. As before, we compile and link with the coverage flag. We run the test. And then we collect the coverage data for both tests using lcov. When you run lcov, you can have it check one test, all tests, several tests. And in this case, we're saying capture everything in this particular directory. So all of our GCDA files. Then we generate the HTML output using gen.html again, and we get this. So we're going to pull up iseven.hpp again. And we see that this time all lines of this code have been executed. We called the function twice, we checked the condition twice, it was true once, and it was false once. So at this point, you might be thinking that this is all fine and good for my tiny little example that fits on one slide, but how would it work on real code? So we're going to run it on some real code. We're going to run it on XSDK Trilinos, which is one of the newer packages of the Trilinos library. It was developed at Sandia National Labs as part of the IDEAS project. It contains the interfaces between Trilinos, Petsy, and Hyper, and it's available at that website. Go download it, have fun. It has 10 automated tests that are run nightly. 6 of them, as before, I mentioned that you can take examples and convert them into tests. 6 of those tests were actually examples that I just added a condition to, and now they're tests. So I want to determine, did I leave anything out? OK. As before, we compile and link with the coverage flag. Trilinos uses CMake, so we're going to modify our CMake configuration file. And all that happens is we insert a coverage flag in our CMake flags here. We build Trilinos in the traditional way. How you build Trilinos is you run your configuration file, and then you type make. And Barry mentioned before that you can do a parallel make. That's what this -j is. We're going to do a parallel make. This also builds the XSDK Trilinos tests because the configure file included the lines for enabling testing. Now we run the tests using ctest. And it's important to note that this is not prohibitively slow. Those tests are each taking a couple of seconds. And this is a real code. So it took 30 seconds total to run our test suite. And all of the tests passed, which is a good sign. Now that we've run our tests, we collect the coverage data for the tests using lcov, and that's the exact same line we had before. Nothing has changed. The only thing that's different is now we have more files that are being processed. And since this step is processing 634 files, it takes a couple of minutes. And when I say a couple minutes, I mean it really did take maybe 3 or 4 minutes. We generate the HTML output using gen.html once again. And this also takes 3 or 4 minutes. OK, so we end up with this code coverage report. And we're seeing a lot of red, which isn't great. We're going to look at one of these files, Balos Petsy Solver Manager.hpp. And that's the solver interface. What that file is, you learned about Petsy. You're aware that it has Krylov solvers in it, KSP. OK. In Trilinos, we have a class called Balos, which is very, very similar. And Balos has a wrapper for Petsy that I call Balos Petsy Solver Manager.hpp. And that's all that file is. OK. Here's the last function in that file. This function is meant to apply a preconditioner to a vector. And even if you can't read all of these lines of code, you can notice that one thing is highlighted in glaring, horrible, ugly red, meaning that is a particular piece of code that is never getting executed by any of the tests. So if we zoom in on it, that is the step that does either the left or right preconditioning. What did I forget to test in this function? I think I heard right preconditioning. I never tested the right preconditioning branch. I have absolutely no idea if the right preconditioning branch works or not. That's something that we need to add a test for. So before we move on, I want to give you a disclaimer about code coverage. These tools, gcov and lcov, they will give you a percentage of code coverage. And if it says 100%, that does not mean that your code is completely bug-free. You can still have tests, and maybe they're just not good tests. But what I'm getting at is gcov and lcov, they do what they do. They're only good at identifying parts of the code that you are not testing. They will not tell you that your code is bug-free. So the last thing we'll talk about is software verification. Why is this a separate topic? Hi.
When you think about the unit tests, for example, how do you actually test something which is running not in serial, but like tenfold parallel?
Trilinos has tests that run in parallel, and as long as you're able to run MPI on the machine that you're testing on, then it's not a big deal. You can just spawn your MPI processes and run your test.
Is every of those tests implemented as one single program, or is that part of a framework?
The question was whether each of our tests are run independently, and yes, each of the tests are run independently. So why is software verification a separate topic? Code verification uses tests. It is more than just a collection of tests. It's an entire process through which you ensure that your implementation shows the expected behavior, and that it's consistent with your model, and also that the science you're trying to do with the code can actually be done. There are many different stages and types of verification during your initial code development. First of all, you want to make sure that your algorithm is stable and accurate, which has nothing to do with testing. It just has to do with the design of your algorithm. You want to make sure that your algorithm is matched to the model that you're using, and you want to make sure that your algorithms are interoperable. In the later stages of the code development, you have ongoing maintenance, and you need to make sure that you are preparing for production. If you're refactoring, you need to make sure that your behavior remains consistent and expected, and I believe Anshu is going to be talking about refactoring right after this talk. Hi, Anshu. All stages have a mix of automation and human intervention. In the development phase, development of tests and diagnostics goes hand in hand with the code development. It's non-trivial to devise good tests, but it's very important. Code is only good as its tests. You want to compare against simpler analytical or semi-analytical solutions, as I mentioned before. They can also form a basis of unit testing. So in addition to testing for correct behavior, you also want to test for stability, convergence, or other such desirable characteristics. So maybe your code works with a particular data set, but you need it to work with ill-conditioned data. Many of these tests will be worth preserving for the maintenance phase. In the mature phase, a subset of the tests developed during the development phase will become part of the regular testing regime. And you want to focus on both code and functionality coverage. As I said before, code coverage by itself does not guarantee correctness if the many moving parts do not also interoperate well. If you modify one part, you can still get correct behavior in all of the individual parts, but not when they work together. So this goes back to what we were talking about before with the unit tests versus other types of tests. You need all of those types of tests. When new features or capabilities are added to the code, some of the tests will have been generated during development, but the capabilities should have been verified for interoperability with the existing code. And a subset of all these tests should get included in the test suite, following the same principles of code and functionality coverage. Other phases are preparing for simulations and refactoring. So selecting tests. The selection of tests is non-trivial. Tools exist for code coverage, which I showed, but not for interoperability coverage. There are no tools right now that will show you whether you are adequately testing interoperability of your different things. So one approach is to use a matrix, as the authors did in the paper cited below. In that matrix, you can list the infrastructure components in rows and the science components in columns, or any type of other components. You list the interoperability constraints and then pick tests. So you want to have tests for ongoing productions and tests that are known to be sensitive to perturbations, because we talked about stability analysis. You want the least complex test that can cover the empty spots, because if you end up with this gigantic testing suite that takes 40 hours to run, then that's not practical. You also want the least complex tests that meet the missing interoperability constraints. So here's an example table from Flash, where we have the infrastructure components in the rows and science components in columns, as I mentioned. And these are the different tests here. We have 4 different tests. A test on the same row indicates interoperability between corresponding physics. So in the first row, that signifies that hydro and burn are interoperable, along with the other 2. The similar logic applies to the tests on the same column for the infrastructure. And I think the only case where there are several in the same column is gravity. Both AMR and multigrid are being tested for interoperability. This is not a complete table, but it shows you basically what the table would look like.
Can you comment a little bit on pre-processing, post-processing in addition to tests, or is that not?
Pre-processing and post-processing in tests. What do you mean?
So I guess you would test the inputs and the outputs of your function in the codes, make sure they're not, say, ints or nans going in?
Oh, yes, you can absolutely test for things like that. So in Trilinos, we have several tests that determine when a code should throw an exception, that it does throw an exception. Is that what you're talking about? Okay. So we have tests in Trilinos where if you give us garbage input, the code should do a certain thing. It should throw an exception maybe. And we have tests that make sure that the code does throw that exception. Good question.
So I wonder, in normal software developing process, will you try that the person who programmed this function is different from the person who designed the test for that function? Will you separate the task to different people?
Okay, so the question was, in normal software development, should the person writing the tests be the same person who wrote the code that it is testing? That's right?
Or should it be different person?
Or should they be different people? At Sandia, I think for the most part, the people writing the tests are the people writing the original tests are the people who developed the code. But as people end up needing more and more things out of the code, then the people who need particular features end up writing tests for those features. Does that make sense?
Yeah, because I have some our group encounters some problem that, like, if I design a function, I know that function, how that function works. Mm-hmm. So when I design the test, probably there are some cases I never consider about that.
Yep.
Yeah. So if there's somebody, they can do tests they can design tests for my function. I think probably they can consider more different case for my test.
Yeah, that's accurate. There will always be use cases that you wouldn't potentially consider yourself, but if they're important to somebody else, then they will bring them up.